Everyone. You're tuned in to the next chapter of our podcast journey through principles of electric circuits. And today we kick off chapter 18, passive filters, a topic that might sound low key, but it's foundational in electronics. So when we say passive, we're not talking about quiet students or shy circuits. We're talking about circuits built entirely from resistors, capacitors, and inductors. No active elements like transistors or op amps. And yet, these passive players perform a very powerful role. They shape the signals. So imagine that you're listening to music with no bass control or a radio that can't tune out noise. Passive filters are behind the scenes. They make sure that the right frequencies get through and all the unwanted ones get filtered out. So in this chapter, we're going to break down low pass filters, which let low frequencies glide through like a bass groove. High pass filters, which block lows but keep your treble real crisp. And band pass or band stop filters, they target just the right range and instead of eliminating everything entirely, they'll target just a very narrow range. And we'll do it using real world circuits. Huh. Real world circuits. Um, and we'll look at frequency response graphs and, of course, the math. That's what makes it all work. So, if you ever wondered how your audio equipment knows what to cut, what to keep, uh, how your cell phone mic cancels out background noise, buckle up because passive filters are the unsung heroes. Let's go ahead and dive into the signal path up next. Low pass filters, slide one of two. All right, listeners, welcome. And today we're putting on our sound engineering hats to explore the low pass filter. Picture this or imagine this: you're at a concert, but you only want to hear the deep bass lines and those warm, mellow notes. The low pass filter is your backstage pass, letting only the low frequencies through and politely showing the high ones the exit door. So as you can see in the graph here, the filter maintains a consistent output V sub out for the lower frequencies, but as the frequencies climb past a certain point, something interesting starts to happen. At the cutoff frequency, that's you see that they're labeled V sub C, the output starts to roll off. It's where the high frequencies begin to get attenuated, or in plain speak, they just get turned down. The horizontal dashed line you see there, it marks that 70.7% of the voltage in, which is that standard reference for defining F sub C. Any frequency higher than that, well, it's getting filtered out, and we call this the stop band. Again, like a bouncer at a club saying, sorry, you're too high frequency for this joint. So why is this important? Low pass filters are used in audio electronics, data smoothing, and again, my favorite, biomedical devices to remove noise while preserving the signal of interest. Next up, we're going to look at how this plays out in a real circuit. So stick around, um, and I'll see you where the schematic magic begins. Continue on, you frequency frequent travelers. Let's pick up where we left off. So we're still tuning in to low pass filters, but now we're zoning in on two key terms: pass band and critical frequency. So the pass band is like the express lane on a highway. It's the range of frequencies that sail through the filter without any resistance. Think of it as the VIP section where frequencies are allowed to party without any kind of interruption. And now what happens at the edge of this party? Well, that's where the critical frequency comes in, also known as the cutoff frequency. It's also designated as the negative 3 dB point, right? So at this frequency, the output voltage has dropped to about 70.7% of its original strength of Vn. And why? Well, if you look at the graph, you'll see a smooth roll off beyond that F sub C. This is where the filter starts muting the higher frequencies, shrinking their influence in the circuit or your signal. So again, to recap all of this, everything left of F sub C, that's your pass band. Everything to the right, that's the stop band, where frequencies are turned away at the door. So go ahead and stick with me. Next, we'll dive into how these filters are built and used in real world circuits. It's time to go from theory to schematic. So stay tuned. And continuing on with our passive filter series, in this segment, we're turning up the volume, literally, because we're talking about decibels. And so, what is a decibel or a dB? If your math teacher didn't explain this to you thoroughly enough, let's go ahead and go over it here. It's not like a volts or ohms. It's not a unit like that. It's a ratio. So it's a way to express how much one quantity has changed compared to another. And most often in electronics, it's about power and voltage levels. So here's the basic power equation in dB. dB is equal to 10 log of power out over power in. So I'm going to say go ahead and memorize these for now, right? This tells us how much output power compares to input power. Now, since many circuits deal with voltage and assuming equal impedance, we can use a slightly modified form of this for voltage, where dB is equal to 20 log V out over V in. And there's a similar one for current. dB is equal to 20 log current out over current in. And that 20 instead of the 10 comes from the fact that power is proportional to the square of the voltage. It's math, that's it. Not magic, but math. Um, and it's what lets us read a filter's gain or attenuation directly from a plot. And because it's a ratio, the decibel is dimensionless. It's a pure comparison. If we look at a 3 dB drop, that just means that your voltage has fallen, sorry, to the 70.7% of that starting value. So is any of this sounding familiar? Hopefully it is. And that's our critical frequency from earlier. So next time you're reading a filter spec sheet or plotting frequency responses, you know exactly what those dB markings mean. So stick around. We got high pass filters coming up next. Let's flip the script on frequency. It's time to stretch out our logarithmic scales and zoom in on one of the most powerful tools in filter design, the Bode plot. Okay, now, if Decibel taught us how to speak the language of gain and loss, the Bode plot teaches us how to map that story across that frequency domain. A Bode magnitude plot. It's a semi-log chart, and that means that frequency on the x-axis is logarithmic, and gain in decibels is linear, and that's on the y-axis. It's a perfect tool for analyzing how a filter behaves over a wide range of frequencies. And I'm going to break it down for you here. So in the example, we have a low pass filter. It rolls off at the critical frequency f sub c. And again, remember, that's where the gain drops to negative 3 dB. After that, the filter begins to attenuate more rapidly. You have a classic roll-off rate for an RC or an RL filter. If you didn't know what that was, a classic roll-off rate is negative 20 dB per decade. So that's how many dB is decaying per decade. Right? Every time the frequency increases by a factor of 10, the gain drops by 20 decibels. You're going to often see two lines on the plot. The ideal line, which is sharp and perfect, like a digital guillotine, and then you're going to have the actual line, which bends a little more naturally because, well, really the components, again, we said they're not perfect, right? So why does this matter? Why should it matter? Well, because the Bode plot gives you instant insight into how much a filter attenuates signals beyond that cutoff frequency and how sharply it transitions. And that's pretty crucial when you're designing circuits that need to respond predictably. Okay, with that said, coming up next, we're going to talk about how these plots evolve in more complex filters and how designers tweak their responses. So go ahead and stay tuned, pun intended. Okay, the Bode plots, slide 2 of 2. So welcome back, filter fanatics. That's what we're talking about today. In our last segment, we explored the Bode magnitude plot and how filters manage signal strength across the frequency domain. But now we take it one step further into the realm of phase. So what we see here in this slide, what it does, it brings us into the world of the phase plot, the second half of a complete Bode diagram. So what are we looking at? Um, of course, the publisher uses LT-Spice, and you can do this on Multisim. So what you're seeing is an LT-Spice simulation. Again, you can do the same thing on Multisim. You're going to see a dual-axis graph, and it shows both the magnitude response. In this case, you see that in the solid red line, and you're going to see a phase response, which is denoted in the dashed red line. So as frequency increases, the magnitude line shows us how the how the amplitude of that signal drops, just as we expected from a low pass filter. So notice how it rolls off sharply past that cutoff frequency f sub c, and it's going to be right around that negative 3 dB point. That's classic, right? So the phase plot, it tells a subtler story. So as frequency increases, the phase of the output voltage lags behind the input. It starts close to 0 degrees, then dives to that negative 90 degrees as we approach those higher frequencies. And this phase information, it tends to be critical when timing really matters, like in communication systems or analog signal processing, because phase shifts can cause distortions or even cancellations with when you have multiple signals combined. So just remember that a full Bodie plot analysis doesn't just show how loud the signal is, it shows when it arrives. And up next, we're going to put these tools to work on practical filters, and we're going to uncover how to design smarter, faster, cleaner circuits. So don't touch that dial. Low pass filter circuits, slide 1 of 3. Welcome back, listeners. Today, we're building on our understanding of filter behavior by exploring the actual circuits that make low pass filtering happen. So if you've ever wanted to know how to let the bass through and cut out all that hiss, this is the place to be, or this is where we're going to get what you want to know. So on this slide, we're looking at two fundamental ways to create low-pass filtering using either RC components, which is just a resistor and a capacitor, or RL components, which is a resistor and an inductor. And I'm going to break this down for you. The RC low-pass filter. So go ahead and imagine this. You've got a resistor in series with a capacitor that heads straight to ground. Um, and your input voltage, V sub in, hits the resistor, and you measure your output V sub out across the capacitor. So as frequency increases, the capacitor starts acting like a short and pulls the signal away from the output. So it starts getting attenuated, in other words. And that's how it filters out high frequencies. The critical frequency or the cutoff frequency, we can calculate that with the formula F sub C is equal to 1 over 2 times pi times R times C. And we can do the same thing with an RL. So the RL low pass filter, right? So in this version, an inductor takes the front line with a resistor going to ground. So you measure the output across the resistor, and what happens to the high frequencies? So the inductor says, no, thank you. It blocks them. But lower frequencies, they glide through, and it's just easier for them to move through. And again, the critical frequency for this is going to be F sub C is equal to 1 divided by 2 times pi times L divided by R. All right, so remember here, or note here, that the inverse roles of capacitance and inductance, you get a perfect complement in the frequency domain. So both filters are great entry points into analog signal conditioning. So whether you're building like an audio equalizer, if you're building an oscilloscope probe, or you're smoothing out a signal for sensors and your microcontroller, these circuits are the workhorses of that. Okay. So coming up next, we're going to compare performance and response of these configurations under real world signals. So stay with us. Low pass filter circuits, slide 2 of 3. So welcome back to our continuing journey into passive filter design. In the last segment, we explored the RC and RL circuits that form the backbone of low-pass filters. Now let's dive a little deeper and let's talk math. So this slide answers a fundamental question. How much of the input signal actually makes it to the output at any given frequency? And it's all about the voltage divider. This is a concept that we've seen before, but now we're applying it to frequency-dependent components. So if we look at the RC low-pass filter, we use the formula V sub out or V out is equal to X sub C divided by the square root of R squared plus X sub C squared, all that times voltage in. So here X sub C is the capacitive reactance. And again, as frequency increases, X sub C decreases. This pulls down the output. So that's your classic roll-off behavior. For the RL low-pass filter, there's a twist, right? So V out is equal to R divided by the square root of R squared plus X sub L squared, all times V sub in, or voltage in. And so with inductive reactance, X sub L, it increases with frequency. So the output drops off as the inductor starts to dominate, just like in the capacitor, but in the opposite way. So the key takeaway here is that both circuits filter high frequencies, but they do it using different reactive tools. So we're building up a real world applications. This is going to be handy when we talk about things like audio crossover networks, power supplies, and signal smoothing. So all of this depends on understanding how voltage responds across a frequency sweep. So stick around because in the next segment, we'll put it all together and discuss phase response and energy dissipation. Don't miss it. Low pass filter circuits, slide 3 of 3. Welcome back to our continuing dive into low pass filters. And so far we've covered amplitude responses and formulas, but now it's time to uncover the phase response, the part of the story that tells us how signals shift in time. So the big idea here is lag networks. So whether you're using an RC or an RL configuration, both types of low pass filters act as lag networks. LAG, lag networks. I don't have an accent and it's hard to understand, but yeah, I'll try to enunciate these things a little better. So that means that uh, they delay the output relative to the input, especially as frequency increases. And here's the key takeaway here. At the critical frequency, both circuits introduce a phase shift of negative 45 degrees. And that's halfway between no shift and maximum shift. And why is this important? Well, let's say that you're processing an audio signal. If different frequencies shift by different amounts, it can distort the waveform. It's called superposition. Right, so understanding where negative 45 degrees happens is very crucial to system design, especially in communications and especially in control circuits. Now let's talk about the phase plot. Notice that smooth downward curve. Right? So that's the phase response. As frequency rises, phase shift dies deeper and it approaches that negative 90 degrees at higher frequencies. So for the RC filter, the capacitor impedance drops, causes more signal to drop across the resistor, and then the output lags. For the RL filter, the inductor's impedance rises, forcing current, and therefore the output to shift with it. Both get to that negative 90 degrees, but they pass through the negative 45 degrees right at the cutoff frequency. So in the real world, this matters for analog synthesizers, audio crossovers, timing networks. If your signal gets delayed too much, things start falling apart. So when someone asks why we care about phase shift in a simple RC circuit, you can smile and say, because timing is everything, right? Okay, so with that said, up next, we're going to turn our focus to high pass filters and how they flip the story on its head. So stay tuned. Okay, let's go ahead and look at this LT Spice simulation here. Oh, and hi everyone, welcome back. In this segment, we're blending a little theory with simulation. And again, you may have heard of LT Spice, but again, we use Multisim here. Or Multisim or LT Spice is fine. Uh, this is an essential tool in every circuit designer's digital toolbox. So today we're going to use it to visualize what we just calculated, which was that critical frequency and the phase shift in a low pass filter. So going from math to simulation. So let's go ahead and break this down. They give you a resistor R at 1.5 kilo ohms, and they give you a capacitor, which is C, at 0.022 microfarads. When you plug those values in into the cutoff frequency formula, you get F sub C is equal to 1, right, divided by 2 pi RC, and that's going to be 4.82 kilohertz. And this is the frequency at which the output drops to 70.7% of the input, right where that negative 3 dB point shows up in our magnitude plot. Inside the Bode plot, the simulation window, that gives you two things. The magnitude response showing how the amplitude of the output drops off, and the phase response showing how the signal shifts in time. So if you zoom in to that phase plot, you'll see a negative 60 degree shift right around that 8.4 kilohertz. That's beyond the cutoff, where the lag gets more pronounced and timing begins to really matter. So in this simulation, again, it's not just some fancy graph. It's an engineering insight. It's a canvas. It's an image that gives you insight. And what the simulation does, it helps you to predict behavior without breadboarding, adjust components to meet design specs, and visualize how your signal will evolve across frequencies. So it turns your math into motion. And we're going to close up by saying that if someone asks, why does it matter if we simulate? Well, just tell them this. because a circuit on paper doesn't sing, but a circuit in simulation, well, that sings in decibels and degrees. So again, I am extending our art comparison from symphony now to singing, right? From painting to writing poems. It's engineering is just an art. It's a quantified art. I'll say that. So anyway, stay tuned because next time we're going to reverse things and we're going to go into the high pass filters and see what happens when low frequencies get the boot. I promise you, it's coming. Pass filters, slide 1 of 6. Welcome back, curious minds. In today's episodes, we're flipping the spectrum, literally. So we're diving into high pass filters, and if you've ever wondered how your audio system cleans up that low frequency hum, this is your answer. So what is a high pass filter? A high pass filter is the gatekeeper of your circuit's frequency domain. So it lets high frequency signals through, clean, crisp, undistorted, while it gently or sharply attenuates those low frequencies. So imagine it like an audio, again, bouncer. If your signal frequency is too low, it's not on the list. But if it's got the right energy, enough frequency, it gets through. So it's important to understand the curve. Let's go ahead and take a look at this graph. The horizontal axis, that's frequency, right, denoted by F. The vertical axis, that's the output voltage, denoted by V sub out. And at first, the frequency is low, right? Output is nearly zero, but as we approach that critical frequency, that F sub C, what happens? Boom! The filter starts letting more signals through. By the time we're past F sub C, that critical frequency, the filter hits its stride and we're back up to full strength, almost matching the input voltage. And let's talk about cutoff in action. So that cutoff point, that 0.707 times the voltage in, or remember, it's also the negative 3 dB point, negative 3 dB point, right? It isn't just a line on the graph, it's a design target. So that's where we define the boundary between reject and pass. So again, know your boundaries if someone ever tells you that. So to the left of it, we have frequencies that are rejected. To the right, frequencies that are passed. And it's all about shaping your signal for whatever task you have at hand. So whether you're audio filtering, and I think audio filtering we can probably relate to more because everyone here probably listens to music and you have some affinity for like bass sounds or treble sounds depending on the type of music you listen to. And so audio is a pretty good example. But it's also useful for things like data transmission and also important for things like power management. So let's go ahead and wrap up this slide or this segment of this podcast and talk about why this matters. Because understanding your circuit um, or understanding what your circuit rejects is just as important as knowing what lets it in. So again, knowing what it lets in only tells you part of what the circuit operation and behavior. So you got to know both. So with that said, again, stick with me because we're going to continue exploring how to calculate that critical frequency and see the circuits that make it all happen. So stay tuned. Pass filters, slide 2 of 6. Alrighty, folks, welcome back to our series on signal filtering. In the last episode, we opened the door to high pass filters, and now it's time to take a closer look at that pivotal concept that defines the action, the critical frequency. So, what is the critical frequency? So, the critical frequency, again, we label it as F sub C. It's the boundary line, right? Boundaries. It's the point where your filter begins to hand off more and more of the incoming signal. Technically speaking, it's the frequency at which the output voltage drops to, remember that number, 70.7% of that input voltage. And in decibel terms, remember this number. It's that negative 3 dB point, right? So the negative 3 dB, negative 3 dB point and 70.7% of the input voltage. They're describing the same point. Again, it's the golden standard in electronics. But what happens at that critical frequency? So let's look at the graph. So below the critical frequency, your signal is being blocked, it's being attenuated. At exactly that critical frequency, you get 70.7% of your input. And as you go higher, the filter opens wide, letting the signal through nearly unimpeded. And think of it like a drawbridge. So at the critical frequency, the bridge is halfway down and letting some traffic cross, but it's still blocking enough of to slow things down. Uh, and again, this matters because the critical frequency defines your filter's responsiveness. It tells engineers, which you all are and will be, where that magic starts. So it tells you where low frequency interference starts fading, and it's useful at high frequencies to get information to shine through, right? To come through. So whether you're like tuning an amplifier or you want to clean up sensor data, or let's say you're building a wireless transmitter, understanding that critical frequency is mission critical. With that said, coming up next, we're going to roll up our sleeves and we're going to calculate some critical frequencies from real world circuit components. Again, we're going to look at resistors and capacitors and inductors, and we're going to look at some loads. So let's go ahead and make this theory come alive on the bench. Stay sharp, stay tuned. Pass filters, slide 3 of 6. So, hey there, listeners. Today we're comparing how high pass filters come to life using real world circuit components. And you've probably heard of RC, RL circuits before, maybe, right? If you're just tuning in, maybe not. But if you've been following along with this entire podcast series, you have. But did you know that both can be used to build a high pass filter? If you were here for when we used both of them to design a low pass filter, then you're probably not that surprised. If you're just tuning into this slide at this point in the podcast, then you're probably thinking, wow, I didn't know that. And I'm going to break that down for you. So again, two pass, same goal. The RC high pass filter and the RL high pass filter. So with the RC high pass filter, the industry and the design of the circuit, the capacitor comes first, the resistor comes second. And what about low frequencies? Well, they're blocked by the capacitor. And what about high frequencies? Well, they flow through just like a cool summer breeze. Um, and then the RL high pass filter, right? So in that one, the configuration is opposite. The resistor comes first, and then the inductor goes to ground, right? So at low frequencies, the inductor behaves like a short circuit, so bye-bye signal. And then at high frequencies, the inductor's impedance just skyrockets, so the signal goes to the output instead. And when you want to find the critical frequency, here's the formula. Well, they're on the slide. So for the RC circuit, F sub C, right, the critical frequency is equal to 1 divided by 2 times pi times R times C. And then for the RL circuit, the critical frequency is equal to 1 divided by 2 times pi times L divided by R. Same idea as we talked about in the low pass filters, but again, applied in reverse. So if we use both the relationship of X is equal to R, where X is the reactance and of the reactive component, it can be X sub C or X sub L. We can solve for this. And here's a good kind of a memory hack to help you remember this. Think of the RC high pass like a toll gate. Um, and the capacitor blocks the slow moving, low frequency traffic, and fast ones zoom right through to your output lane. All right. So with that said, we're going to wrap that up here for this slide. Coming up next, we'll explore how these filters behave in real time. We're going to look at their output voltage curves. If you're a hands-on learner, this is your moment. So stay locked in. High-pass filters, slide 4 of 6. Welcome back to our journey through passive filters. Now that we've built our high-pass filters with RC and RL components, let's explore what happens to the signal as it travels through. I should try to do like a Neil deGrasse Tyson. Using something we electrical nerds love, math. Yep, we're talking voltage divider equations. How output voltage is calculated. Whether you're working with capacitors or inductors, your output voltage just about depends on how resistance, which is denoted by R, and reactance, denoted by X, balance each other at a given frequency. Oh, I think I can do a Neil deGrasse Tyson. All right. So let's dive into each case. The RC high-pass filter equation. This is where, look at the slide, V out is equal to R divided by the square root of R squared plus X sub C squared, all multiplied by the voltage in. Again, this is a ratio of the voltage in. And here X sub C is the capacitive reactance, being equal to 1 divided by 2 pi Fc. At high frequencies, X sub C becomes small, and the voltage out is approximately the voltage in. At low frequencies, X sub C is large and the V out drops off. Now let's look at the equivalent or the cousin of this, the RL high pass filter equation. Here we see the equation as V out is equal to X sub L divided by the square root of R squared plus X sub L squared. Again, this ratio multiplied by the input voltage. Again, the XL here, the inductive reactance, is equal to 2 pi FL. If you look at it, it's directly proportional to frequency. So this inductive reactance increases with frequency. At low frequencies, X sub L is tiny, so you have a low output. But as the frequency climbs, XL dominates, and you have a high output. And how do we translate this to real life, to space, to the universe? Think of these circuits like volume knobs tuned to your favorite stations. The RC filter says, I'll let that fast stuff, the high frequencies, pass through. Why that RL filter says, slow signals, you're not getting in. And both are governed by these voltage divider formulas, helping you design circuits that are smart and selective. Next up, how phase behaves in high-pass filters and why that negative 45-degree point is a big deal. Stay tuned, my friends. That was the best Neil deGrasse I could do. All right, let's go ahead and continue with high-pass filters. This is slide 5 of 6. So we're back with the wired force sound as we trace the path of signals through the elegant corridors of high-pass filters. I'm getting good at this. Again, so far we've seen how they let high frequencies through and how they suppress the slow stuff. But now let's talk about what's happening with the phase, because filters don't just affect how much signal gets through, they also shift when it gets through. So let's talk about the phase response. In both the RC and the RL high pass filters, the circuit is what we call a lead network. And that tells us something very interesting, that these circuits advance the signal's phase. So they literally push the voltage response ahead of the input. Again, I'm going to break this down for you. At low frequencies, the phase shift is close to 0 degrees, so that's almost no shift, right? Nearly no shift. But at high frequencies, the phase shift approaches plus 90 degrees, and that's like a full quarter wave lead. But again, there's the sweet spot, that critical frequency or that cutoff point frequency F sub C, where the phase shift is plus 45 degrees. And you look at the graph and see what it tells us. Again, looking specifically at the phase curve on the slide, as frequency increases, so does the phase shift. So it bends smoothly toward that 90 degrees. And at that exact midpoint, the critical frequency, F sub C, you'll find our positive 45-degree marker. There's a symmetry to it, to the low-pass filter phase plot, just flipped. Remember that lag becomes a lead. And if you're looking at a real circuit visual, right here on the left, we got a capacitor that comes first, right, in the RC filter. And on the right, an inductor where it comes second, right, for the RL filter. So the reactive components are in different places is basically what you need to get out of that. But in both cases, resistance and reactance combine to create this phase effect. So what's the main takeaway here? If you want to speed up your signal's response, or if you want to shift it forward in time, a high-pass filter just might be what you're needing. And a 45-degree cutoff frequency, critical frequency, that's the handshake where frequency response and phase align in perfect sync. All right. So with that said, go and keep staying with us. Our last high pass filter slide is coming up, right? Because this one's 5 of 6. Next one is 6 of 6. And thank you very much. I'll see you in the next slide. I'll see you on the other side. High pass filters, slide 6 of 6. Okay, welcome back to our final chapter in the story of high pass filters. We've explored the theory, the math, the phase response, and it's time to bring it all together in a real circuit example. So let's look at the example we have here, the circuit and the calculation. So take a look at this RC high pass filter. We've got a 0.068 microfarad capacitor and a 27 kilo ohm resistor. Don't forget our trusty formulas, right? So F sub C is equal to 1 over 2 times pi times R times C. So just plug in the numbers, plug and chug, and we land on a critical frequency of 86.7 hertz. And that's the point where our output, remember, hits at 70.7% of its maximum amplitude. That's the gateway between rejection and transmission. So this is simulation in action. Below the schematic, we've got a Bode plot from Multisim. Again, really, really cool tool. You know how to use it by now. It'll be your best friend. Can't wait till they have Multisim on a mobile device like a phone. Anyway, take a look at that graph, and what do you see? You see a smooth curve climbing through the low frequency silence into the high frequency passband. So the cursor is placed right at our calculated critical frequency, the F sub C, and we see that it's 86.693 hertz at that negative 3, in this case, negative 3.01 dB. A good point for lab is you might not be able to get your cursor right at that 3 dB. Just get as close as you can in the lab. But again, that's close enough for us to be on target. And it's close enough to confirm by practice the theory that we've been learning. And the main takeaway or the final takeaway here would be that um, the filter behavior from both the math and the simulation perspective give you a better understanding of the circuit. So whether you're going to prototype something like a guitar pedal or design wireless comms, the high pass filter, again, that's the frequency gatekeeper. You can use tools like Multisim, and then the author here uses LT Spice as well. Um, you don't need a lab bench to verify your designs. You can visualize performance just with a few keystrokes and a simulation. And that's it for this slide. What we're going to do next is we're going to switch gears and look into the bandpass filters, and we're going to get into combining high and low pass to isolate just the frequency window. So don't miss it. This is where selectivity really shines. Oh, and one more note. They sell these kits for guitar pedals, and I really want to buy one. And it might be too late for this course, but build a guitar pedal and actually break that circuit down as we solder it, put it together, test its behavior. So with that said, I'll see you on the next slide. Band pass filter circuits, slide 1 of 2. Hello again, and welcome back to Principles in Practice. Today's episode is all about frequency selectivity and how we shape signals, not by letting everything through, but by letting just the right band pass through. And that's where we get that band pass term. We're talking about band pass filters. So we sort of tune into the middle of a frequency band. So imagine you want to listen to just one radio station and you want to ignore all the others. That's kind of what a bandpass filter does. It lets the middle range of frequencies pass, and it rejects the high and the low ends. So think of it like and again, audio bouncer. I'll come up with a different analogy. Too many bouncers here, but this will be yeah. Anyway, so think of it like an audio bouncer. And what the filter does, it only frequencies that have that right ID can get in. Imagine you're going to a club and you have to be a certain age to get in. So let's say you have to be over 21. But let's say this is a club that doesn't allow people over 35 or something like that. And it's like, yeah, if you're over 35, you can't come in. And if you're under 21, you can't come in. I don't know if that really exists. It may exist somewhere. But that's the concept of the bandpass. All right, so on this slide, you're going to see two approaches to bandpass filtering. You're going to see a series resonant bandpass filter and a parallel resonant bandpass filter. So let's talk about each one of these independently. So with the series resonant bandpass filter, whew, tongue twister. Um, you have an LC series resonant circuit, and that's placed before the resistor. So at resonance, that LC combination, it has a minimum impedance, and that allows the desired frequencies to pass. So frequencies outside of this sweet spot, they're blocked. If you look at the parallel resonant bandpass filter, you kind of flip that structure, and now the LC combo is in parallel with the output. And off resonance, right, this tank circuit draws current away, it attenuates out of band signals, but at resonant point, it acts like an open circuit, allowing the signal to pass cleanly. And this is important if you're filtering RF channels, again, if you're designing equalizers, or if you're cleaning up sensor signals, bandpass filters are the way to go. So you have two types you see here. Again, the series and parallel resonance. They both give you different tools for different use cases. With that said, keep hanging on there. Stay tuned because we're going to continue diving into how to calculate these resonant frequencies. We're even going to explore our famous or our favorite Q factors and how they shape the sharpness of our filters. Until then, keep your signals clean and your circuits resonant. Bandpass filters, slide 2 of 2. Welcome back, listeners. And now that we've seen how bandpass filters are constructed, it's time to visualize how they perform. And what's today's topic? Well, that beautiful bell-shaped curve that tells us everything we need to know, the frequency response of a bandpass filter. And what exactly are you looking at here? Right? So this plot shows the generalized output response of a bandpass filter. On the vertical axis, you've got the output voltage, right, V sub out. On the horizontal axis, well, you have frequency. And notice that the peak, that voltage max at the center of the frequency F sub 0, that's the sweet spot where the circuit is tuned and where the signal kind of sails through with little resistance or minimal resistance, right? The bandwidth, that's the critical range. If you look at the left and right of that peak, you got two key points, F sub 1 and F sub 2. And the output drops to, on both sides, 70.7% of the maximum. And again, why that number? Again, remember, this corresponds to the negative 3 dB point, and that's just a standard threshold in filter design. So, yeah, if you look at the range between F1 and F2, which is your bandwidth, the frequency window there, that's where your signal is the strongest. The engineering implication to this is that the bandwidth tells us how selective your filter is. If you have a narrow bandwidth, that means that your circuit is sharply focused. It's great for precision, like a radio tuner. If you got a wide bandwidth, that means that more signals get through. It's useful in audio applications or like broadband systems. Again, but the next time you're working on signal processing, remember that the shape of this curve tells the story of what your circuit allows and then what it leaves behind or what it leaves out. Right. So with that said, our next stop is going to be diving into band stop filters, and we're going to explore how to block out those noises literally. Until then, stay resonant and keep filtering forward. Band stop filters, slide 1 of 4. Welcome back to Filter Frontiers. Kind of happy with that name for the podcast. I should go back and redo all of these and make sure they're all titled the same way. Filter Frontiers. That would have been great for this whole lecture. Dang, it's too late now, but I like it. So, Filter Frontiers were signal clarity meets clever circuitry. Today's stop on our journey is, you guessed it, band stop filters, the opposite of bandpass filters that we just looked at. So let's dig in. What is a band stop filter? Think of a band stop filter as, and again, I'm sorry for the analogies because I can't think of anything else, like a bouncer again at a nightclub. And I don't even go to nightclubs. I just seen them on TVs. I've never been to a nightclub that actually has a bouncer that is that prestigious or something. Any place I've ever gone, yeah, no bouncer. Security, yes. Bouncer, no. Security. Hmm. I'll try an analogy with security, but let's go ahead and stick with the bouncer idea. It lets everyone in except for one very specific group, a narrow band of frequencies, right? That doesn't sound good already, but that's the way that club works. So how does it work? So you have two main flavors. Sorry, I'm coming up with a bunch of other examples in my head now. So again, you got two different flavors of this. The series resonant band stop filter, that's the one on the left, and the parallel resonant band stop filter, that's the one on the right. I'm going to go ahead and break down the circuits for you, right? So in the series configuration, we place a resonant LC circuit. It's in parallel with the load, and this LC combo is tuned to the frequency we want to block, right? So at resonance, it creates a very low impedance path. Like a trap door, it just siphons off the unwanted frequency. So they just go to ground. The trap door is actually a good analogy. It's just like puts them to ground. In the parallel configuration, that same LC combo, it sits in series with the path, but at resonance, its impedance shoots up like a wall. So in that case, it blocks the signal right there. It doesn't let anything pass through. And why do we use these? Well, because bandstop filters are essential when you want to remove interference, like one very, 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 very important one for us in medical is the hum that you may get from 60 hertz, and that's coming from the power lines. Uh, and again, may not be a physical hum, but it may just be noise on the signals. So I don't mean like an actual audio hum. Or again, you can tune this to any other frequency. You might have specific tones and audio signals that you want to remove, or even radio frequencies bleeding into unwanted channels, right? So that's kind of like the big takeaway here. So stay with me because next I'm going to talk about how these filters behave across a range of frequencies. And again, a spoiler, uh, they're quite the shapeshifters on a Bodhi plot. Ha ha ha. Okay, remember, it's not about what you let through, but uh, what you leave out. That sounds very stoic. See you on the next slide. Band stop filter circuit slide 2 of 4. Welcome back to Filter Frontiers. In this episode, we're charting the frequency response of one of the most targeted tools in our filtering arsenal, the band stop filter. So let's picture this performance, or let's imagine this performance, right? Um, you have that signature curve, which you see there on the slide. The diagram here is it's a general response or generalized response of a typical bandstop filter. Think of it as a valley that's nestled between two peaks, and you have F sub 0 or F sub naught. That's that center frequency right at the bottom of the valley. And then on either side, we got F sub C. We got F sub C on one side and the other, and these are the cutoff frequencies. Again, the output drops to 70.7% of the maximum at these points. Again, just as a reminder, 70.7% of the maximum voltage in, that's going to be equivalent to that negative 3 dB threshold. So what's actually being measured? That dip that you see, that's where unwanted frequencies are effectively squashed. So like they're just throwing them down uh, that chasm. We can call the span between both FCs the bandwidth from one FC to the other FC, one critical frequency to the other. In this case, FC1 to FC2. And this is the key metric. The region is specifically rejected while everything outside of it flows through mostly unaffected. And this matters because this is incredibly useful when you're trying to eliminate power line interference at some specific frequency. If you need to silence a feedback loop in the audio systems, or if you want to, let's say, surgically remove narrowband RF noise. Okay. With that said, we're going to look at how these filters behave in real world component networks. And again, another spoiler, series and parallel LC combos each tell a different story. Again, stay tuned. Um, no, stay tuned out, stay selective. Band stop filter circuits, slide 3 of 4. Welcome back to Filter Frontiers. In today's Design Lab segment, we're crafting a series resonant notch filter. And notch filter and bandstop filter, it's the same term. They're used interchangeably. If you think of notch like you're just notching something out, it might give you a better visual to stopping a certain band range of frequencies. It's a tool for knocking out unwanted frequencies like the 60 hertz hum that, or the 50 hertz that if you're overseas, from your signal path. So the problem that we're given here is that you have a source voltage equal to 1 volt, and you have a resistor at 100 ohms. You have an inductor where that it's at 70 millihenries, and it has an internal resistance R sub W at 10 ohms. So now that we're dealing with practical circuits, we need to start accounting for a lot of the other real world variables. And the goal here is to reject that 60 hertz noise, right? So we have a question. What value of capacitance C do we need to make that happen? And we can calculate this. This is where resonance comes into play. That center frequency F sub naught for a series resonant circuit, we can determine this by the formula F sub naught, right? It looks like a 0 to you, F sub 0 or F sub naught. That's equal to 1 divided by 2 times pi times the square root of L times C. Right? If you rearrange this formula for C, is just a little bit of algebra, right? C is going to be equal to 1 divided by 2 times pi times the square root of L times S sub naught, and then all of that squared. And then all we have to do is plug in the numbers. So if we're solving for C, we plug in the numbers that we get, the resistor and the inductive value, and the frequency is 60 hertz that we're working with. We come up with a capacitive value of 101 microfarads. And that's it. That's the answer. And so what does this do? This configuration, it creates a notch at exactly 60 hertz. That's going to be where the LC combination presents very low impedance. It pulls the frequency down, it diverts it to ground. Think of it like the trap door, right? Where trap doors send something straight to ground. So that's what's happening at this frequency. Everything else, it flows right past. So that's it for this slide. Stay tuned for the next one. We're going to run through this through simulation, and we're going to visually confirm our theory with a Bode plot. And again, another spoiler. It's um, it's as satisfying as like snapping a puzzle piece into place, right? So it's going to be all these pieces are going to come together if you like doing puzzles, right? All right. Catch you on the next frequency frame. What's the name of that song? Catch you on the. Anyway, catch you on the next frequency frame. And stop filter. Welcome back, signal sleuths. As promised, we've run our notch filter through simulation, and we're looking at the frequency response on this slide. Oh, by the way, this is band stop filter circuits, slide 404. And again, we're going to unpack what the simulation on this slide reveals. You're going to see the green truth, right? The magnitude and the phase. So the solid green line that you see there, that's your magnitude response. The dotted line is your phase response. And what do we see? Right around that 60 hertz, the magnitude line, it dives and it hits about negative 20 dB. And that confirms our maximum signal rejection at that designated notch frequency, which is 60 hertz. So 60 hertz is the thing we're targeting, and we're targeting that with our 101 microfarad capacitor and our 70 millihenry inductor, and that's it. Mission accomplished. There's also a phase behavior you have to look at. If you look at the phase shift, right? It swings sharply as we move through the rejection band. That's typical of a series notch filter. It's another, let's say, a fingerprint of resonant behavior. So you can distinguish that by just looking at the graph. Now, when you're looking at the simulation wraps up this theoretical with the practical, or gets you closer to the practical. Again, you calculated it, you simulated it, and now you can trust it. So whether you're designing for that rejection of the 60 hertz, right, the hum rejection, if you're signal conditioning, because it might be some other frequency, or you're just doing some audio cleanup, this is the kind of precision that makes analog electronics that art form, like I mentioned many times. Okay, and so that's a wrap here on bandstop filters. We're going to go ahead and move on to the world of active filters later on, using operational amplifiers, not in this class, but um, in another class. And until then, keep your waveforms clean and your inductors cool. Stay tuned, stay resonant. So the key ideas, this is slide 1 of 2 on key ideas. And welcome to, what did I call it? Filter Frontiers. Fanatics of Filter Frontiers. Welcome to our summary zone, our recap zone. Recap, capacitor. That sounds better. Welcome to our recap zone. Let's tie up the core takeaways from our deep dive into passive filters with this crisp summary slide. Let's go down the key concept rundown. So we have RC and RL circuits. Those are the building blocks. So whether you're rolling with resistors and capacitors or resistors and inductors, these are the essential combos to shape low pass and high pass responses. We can look at phase behavior, and that tells us a different story. Not a different story, but another part of the story. So in a low pass filter, the output lags behind the input. In the high pass filter, the output leads the input. So there's a subtle phase relationship uh, that becomes a signature fingerprint to signal processing to let you know whether you're high pass or low pass. Um, the roll off reality, we talked about roll off rate. Let's talk about the reality of that. So, the roll off rate of these simple filters is a steady negative 20 dB per decade. So, think of it as the slope of your filter's curtain dropping off those unwanted signals. And if we talk about band pass filtering, right, or frequency tunneling, a band pass filter is, the last time I'll say this, the frequency bouncer. It only lets signals in between two critical frequencies, f sub 1 and f sub 2, and it boots the rest. So this is like the cheat sheet you'd write down on your coffee cup before lab. So whether you're tuning an audio system, whether you're filtering power lines or you're cleaning up a digital signal, these are your rules of engagement, right? So with that said, we got one final slide because this is one of two. And we got that one more slide of ideas that's going to lock this chapter into your mental circuit board. So stick with me, stay sharp, stay analog. Key ideas, summary, slide 2 of 2. So welcome back to the wrap-up wave of our filter journey, you filter fanatics in the filter frontier. So what we're looking at in this slide delivers the final, we'll call them strokes of the canvas of a passive filter, or the understanding of the theory. And let's go ahead and lock in these essentials before we finish with the presentation. So filter wisdom in 4 lines, right? 1, 2, 3, 4 bullets. So we got band stop filters, the rejection specialists. And these circuits, they block a narrow band of frequencies and they pass everything else. You can picture them as sound engineers muting that annoying 60 hertz hum while it lets your music flow. Then the next one is versatility in construction. So when you're dealing with both bandpass and bandstop filters, they can be built from series or parallel resonance circuits. And the trick in the topology is what frequencies you're aiming to filter. Let's talk about bandwidth's best friend. Yes, you got it. That's Q. So the bandwidth of a resonant filter, again, it isn't just a number. It's tied to Q, that quality factor, and the resonant frequency. So if you have a very high Q, you're going to have a very narrow bandwidth. If you have a very low Q, you're going to have broader brushstrokes on your canvas. Don't forget the 70.7%, that golden voltage rule. So at a filter's critical frequency, the voltage of the output drops to 70.7% of its max. That's again, also noted as the -3 dB point, and it's your target when you're setting those cutoffs. So here marks the end of this chapter in this presentation. From low pass mellow vibes to high pass sharpened edges, the bandpass and band stop or stop gap tactics that we use in between your signal path will never look better, right? It will be super clear. Again, that's it. Catch me on the next episode when we dive into active filters and op-amp magic. Not here, of course, in the next course. Well, since not in this class, but in your next semester course. That makes a little more sense. Until then, stay filtered, stay focused. All right, let's go ahead and wrap up with some key ideas. This is slide 1 of 3. The key terms that we've discussed in this lecture are the low pass filter. So this is a type of filter that passes all frequencies below a critical frequency and rejects all frequencies above that critical frequency. The next term is pass band. This is the range of frequencies passed by a filter. The next term is critical frequency, denoted by F sub C, and this is the frequency at which a filter's output voltage is 70.7% of the maximum. And don't forget the roll-off, the rate of decrease of a filter's frequency response. Key ideas, slide 2 of 3. The next term is attenuation. This is a reduction of the output signal compared to the input signal, resulting in a ratio with a value less than 1 for the output voltage to the input voltage for a circuit. Next term is decade, a tenfold range in the frequency or other parameter. I think we know what a decade is. Next term is Bode plot. Right, so this is a graph of a filter's frequency response showing the change in the output voltage to the input voltage ratio expressed in decibels or dB, and it's expressed as a function of the frequency for a constant input voltage. All right, finishing up with our key ideas. This is slide 3 of 3. The first term on this slide is high pass filter, kind of like what it sounds like. A type of filter that passes all frequencies above a critical frequency and rejects all frequencies below that critical frequency. Bandpass filter. A filter that passes a range of frequencies lying between two critical frequencies and rejects the frequency line above and below that range. Center frequency. Resonant frequency of a bandpass or band stop filter. And then finally, band stop filter. A filter that rejects a range of frequencies lying between two critical frequencies and passes frequencies above and below that range. Come to the portion of our recorded lecture where we go over the self-assessment quiz. So let's go ahead and get started with quiz question number 1. The basic filter circuit shown is a what? Low pass, high pass, band pass, or band stop? Go ahead and pause the video. All right, if you returned, the answer to this question is a high pass filter, or answer is B. Quiz question number 2. For the circuit shown, the output voltage will what? A, lead the input voltage, B, lag the input voltage, C, be in phase with the input voltage, or D, be out of phase with the input voltage. Go ahead and stop the video now. Okay, you are back. The correct answer is B, lag the input voltage. Quiz question number 3. A filter with the response shown is a what? A, low pass filter, B, high pass filter, C, band pass filter, or D, band stop filter. Go ahead and pause the video now. And the correct answer is D, band stop filter. Quiz question number 4. A series resonant filter can be made into a what? A low pass filter, a high pass filter, a band pass filter, or D, none of the above. Go ahead and pause the video. Okay, you've returned. The correct answer for number 4 is C, band pass filter. Quiz question number 5. For the circuit shown, the output voltage at any frequency can be expressed as, and again, I will not be reading the equations. Is it option A, option B, option C, or option D? Go ahead and pause the video. All right, if you're back, the correct answer for number 5 is A. V sub out is equal to R divided by the square root of R squared plus X sub C squared, all inclusive multiplied by voltage in. Quiz question number 6. At the critical frequency, the phase shift of a low-pass filter is which of the following? A, 0 degrees, B, minus 45 degrees, C, plus 45 degrees, or D, none of the above. Go ahead and pause the video now. And now that you've returned, the correct answer is B, minus 45 degrees. Quiz question number 7. The basic filter circuit shown is a what? A low pass, B high pass, C band pass, or D band stop. All right, go ahead and pause the video. Thank you for returning. And the circuit shown is a band stop configuration. Quiz question number 8. At the cutoff frequency, the output of a filter is what? A equal to the input, B negative 3 dB, 6 dB, or D negative 20 dB. Go ahead and pause the video now. Thank you for returning. And the correct answer here was negative 3 dB. Here's question number 9. Again, I'm not going to read all of these. The definition of a decibel is A, B, C, or D. Oh, go ahead and pause the video. All right, you should return by now. The correct answer here for number 9 is C. Both A and B are correct. Question number 10. The measurement until used with decibels is the what? Watt, volt, ohm, or none of the above. Again, A is for watt, B is for volt, C is for ohm, and D is for none of the above. Go ahead and pause the video now. Thank you for returning. The answer in this case is D, none of the above. That concludes this final lecture for this course. Here are the answers to the previous self-assessment we just conducted. Go back and compare your answers with the answer key here. Again, it's not important to know the right answer, but it's important to know the right answer and why it's right. And it's important to know the wrong answers and why they are wrong. So that'll give you a full understanding of any concept. With that said, I want to thank you for your time. This has been a great semester, and I will see you in a new course sometime.